Okay, I have a couple last topics to talk about for the exam 3. One of which is radical reactions involving oxygen. Now, oxygen radicals run the gamut between very stable to very unstable. An example of an unstable radical is a hydroxyl radical. An example of a stable radical is actually oxygen. The oxygen that we breathe actually exists as a diradical. Now, this oxygen diradical will slowly react in radical reactions, pulling off hydrogens off of alkanes or so, but it typically reacts when you have a possibility of forming a really stable radical, and even then it takes a little bit of time. And so this is something that you really should be careful of. Say if you have grease, essentially what can happen with grease over time reacts with oxygen, pulls off a hydrogen, forms a radical, and then this radical then reacts and forms that, which is a peroxide. Now, peroxides are very dangerous because this is a very weak bond, and it's been known to split apart and then starts reacting, creating a generation of a lot of heat. When you have a generation of a lot of heat, you could end up with fire. And so they say not to throw oily or greasy rags in the corner of your garage because they may spontaneously catch on fire. And that's because what happens over time is they form peroxides, and then peroxides just light up. Similarly, if you have a greasy apron with kitchen grease on it, definitely don't put that into a dryer. In fact, that's what happened a few years back, and it burned down the glass nickel on University Avenue. So please be very careful when it comes to grease, and because it has a tendency to react. The other thing you might have noticed is cooking oils have a tendency to go bad, and that's because of this reaction. Some cooking oils, especially those that are unsaturated, have alkenes in them. And what oxygen likes to do is over time it will react got ahead of myself. It will react to form this, and this radical is particularly this hydrogen here is one of the ones that really has a tendency to be pulled off by the oxygen radical. Because it's resin stabilized. And either of these can react. You end up getting a mixture. And let's go ahead and copy that. Move to the next page. This one is here. This one goes here. And then this does other types of chemistry where over time a little bit of heat breaks the oxygen-oxygen bond, very similar to HBr and peroxides. And then this has a tendency to swing its electrons down, and that breaks a carbon-carbon bond. Get another carbon radical, so on and so forth. The aldehyde which is this, has a tendency to be oxidized further, and we won't worry about this mechanism. But aldehydes are oxidized by oxygen in the air to carboxylic acids, and carboxylic acids have a tendency to smell rancid, especially when they're a straight chain, so on and so forth. Okay. If you've noticed an old bottle of cooking oil, there's a little bit of white stuff underneath the cap. Well, that's where residuals of oil have come in contact with the oxygen, and that starts this reaction here, creating compounds like this that have a tendency to be more solid than liquid, and they accumulate. Okay. Hydroxyl radicals are particularly nasty radicals in that they have a tendency to pull off any hydrogens attached to carbons quite quickly. And these are known to cause a lot of cellular decay in terms of it starts interfering with DNA and starts breaking down cells. And so hydroxyl radicals have a tendency to be bad. You might have heard the term antioxidants and how these are there to essentially help minimize the damage of the cellular decay. And the way it does it is a lot of your antioxidants have phenolic type residues. Like one example would be vitamin E. And so just draw up one of the many compounds that answer to the name vitamin E. Whoops. Like so. And what they do is they provide a hydrogen that these hydroxyl radicals like to pull off, mainly this OH one. And you end up with this oxygen radical. This oxygen radical is quite stable. It's not that reactive, and a tendency to not react with things like DNA. The reason for this is, again, you end up with a lot of resonance stabilization. And the more stabilization that radical has, the less likely it is to react any further. Okay. So that's pretty much all I want to talk about oxygen radicals. They're not very good synthetically speaking, but in terms of reactions, these are make for good mechanism problems. Now for cyclopropanes. Cyclopropanes are something that have a tendency to show up on a lot of standardized exams and MCATs, that kind of thing. So I probably want to talk about them. They are useful things, like cyclopropane itself was used as an anesthetic for quite a bit of time. But unfortunately, fortunately, it's been replaced, because it turns out cyclopropane in oxygen mixtures tend to go boom. This highly explosive nature has caused basically the anesthesia tendency to move away from cyclopropane. Okay. Other molecules that have cyclopropanes in them. This molecule right here. We won't worry about the stereochemistry of this cyclopropane, except that's typically a wedge right there. The stereochemistry is ill-defined. It's typically a mixture of that. This is called resmetirin. And this molecule right here is an insecticide. And it's typically used to get rid of a lot of mosquitoes. So blessed be this molecule right here. Another molecule that's pretty important that contains cyclopropane molecule right here. ciprofloxacin, which is a widely used antibiotic. And one other example of a useful cyclopropane molecule, and this one is particularly strained. It's called methyl cyclopropane. This molecule, what it's used for is it's used in the fruit industry. Once fruit is harvested, it's packed into trucks, and then this is sprayed into those trucks. And what this does is it delays the ripening process. And so as a result, fruits stay better for longer periods of time. Essentially, it competes with ethylene, which is the gas that fruit give out that ripens much more quickly. And so this competes with it and delays the ripening process. So anyways, that's all the good stuff that cyclopropanes can do. Now, how to make these things? Well, we have two ways of making cyclopropanes. One method is to take an alkene. Doesn't matter if it's cis or trans. And treat it with chloroform in the presence of a base. And what that does is it creates a dichloro cyclopropane. And this reaction is a very concerted reaction, meaning cis stays cis, trans stays trans. So if the two substituents on the alkene are trans, they end up trans on the cyclopropane. And you get a racemic mixture, because we're starting from a molecule that is achiral, and we're going to a molecule that's chiral. Whenever you do that, you get a racemic mixture. The mechanism of this reaction is chloroform. The hydrogen on chloroform, turns out that's acidic. pKa roughly around 16 or so. And it's acidic because of the inductive effect. All three chlorines are pulling electron density away from the carbon-hydrogen bond, making this hydrogen delta positive. A strong enough base like tert butoxide can take that proton off. And you get a carbanion. Now, this carbanion has a leaving group attached. That carbon doesn't like to be negatively charged, and so one of these leaving groups can leave. And then you get a really interesting intermediate. This molecule, this intermediate, is what is referred to as a carbene. That carbene is different from any other active reactive intermediate we've had, because it is part carbanion due to the lone pair. It is part carbocation due to the empty orbital. And some carbenes react as radicals as well. So these molecules here react as carbanions, carbocations, and radicals. And so they are really an amazing intermediate. So what it does in terms of reacting with an alkene the lone pair on that carbon goes to one of the two carbons. It doesn't matter which one. Then the pi bond goes back up to the carbon to fill the existing orbital. And as a result, in one step, you form a cyclopropane. If you had a cis alkene, you get a 6 cyclopropane. Trisubstitute alkenes, and tetrasubstitute alkenes also will react in these conditions to give cyclopropanes. Product of this reaction if the ethyl group is cis, that means the other methyl group. So if the ethyl group is a wedge, the methyl group being cis to it is also a wedge. The other ethyl group becomes a dash. You get a racemic mixture. Okay. So that's chloroformine base to form a dichloro cyclopropane. The last reaction that we have is called the Simmons-Smith reaction. It's very similar. Again, cis stays cis, trans stays trans. And the reagents to do this are diodomethane, CH2I2, and then a specialized mixture of zinc and copper. It's sort of a zinc copper alloy. Is used. And you get this. We're adding a CH2 across an alkene. What happens in this reaction is the zinc metal inserts itself between the carbon and the iodine. The copper helps just a little bit in this, but we won't worry about the mechanism. and you get this. This right here is what's referred to as a carbenoid. It's not a true carbene. It just has properties of a carbene. What I mean by properties of a carbene? Well, it has a carbon-zinc bond. Carbon is more electronegative than zinc. So because of that bond, it's delta negative. But that carbon also has a leaving group, I, off of it. Because of that, that carbon is delta positive. And so this carbon is both delta negative and delta positive at the same time, giving its carbene type reactivity. And the mechanism of this. Is the electrons from the zinc carbon bond move to one of the two carbons. It doesn't matter which one. And that kicks the pi bond up to the carbon, and that kicks off the leaving group. And this happens in a concerted reaction, meaning the bonds are being formed at the same time. So this alkene doesn't have a chance to rotate, so cis stays cis, trans stays trans. Had a molecule like this. Form a cyclopropane. Has two ethyl groups that are trans to each other. So you pick one ethyl group to be a wedge. If you pick one to be the wedge, then the other one has to be the dash. And then this methyl group is also a dash. Going from achiral to chiral, racemic mixture. Okay. The last thing that we have to cover for the exam is almost pretty much a review. We've covered the addition reactions of H and OH across an alkyne. Such as hydroboration, and this adds anti-Markovnikov, gives you an enol, but enols are unstable. They rapidly become carbonyls. The Markovnikov version involves a little bit of mercury sulfate, acid, and water. That puts the oxygen on the more substituted side. You still get an enol, but that rapidly becomes the carbonyl. Now we covered those. Other reactions that we have. We can add HBr. In this case, it's a Markovnikov reaction. So the H goes on the less substituted side, Br goes on the more substituted side. If it was like something like this, the two sides are equally substituted. So expect a mixture of products. And also, HBr doesn't have any sort of sterile control to it. So you have mixtures of syn and anti-addition. Plus, since the two carbons are equally substituted, you go to both places. The reaction also works with HCl Again, fluorine's going to go on the more substituted side, give you a clean product. Use HCl up. In this reaction here, you'd have the same problem. The mechanism of this reaction is pretty much the same. You can protonate, and you end up forming a carbocation, and then the bromide attacks the carbocation. The bromide attacking the carbocation is not really a reversible process, because leaving groups that we have tend not to leave sp2 carbons. Now it turns out that you can add one equivalent of bromine and stop here. If you add a second deal of HBr to this compound, the product that's typically given is the bromine ends up on the same carbon. You can do this reaction also with HCl as well. Anti-Markovnikov addition of HBr. Mechanism's just the same as the mechanism of HBr across an alkene. The Br goes on the less substituted side, and there is no stereo control, so you get a mixture. Now, if you add HBr and peroxide to these molecules, I have no idea what will happen. I've looked in the literature to find out what would happen, and I have found absolutely nothing. That means that most likely it gives you a complex mixture of products. So just don't add HBr and peroxides to molecules like this. Okay. You can also add Br2 in a non-nucleophilic solvent. The major product you get is with the two bromines trans to each other. The minor is with them cis to each other. You can do it with chlorine as well. The presence of these minor products hint that the mechanism of bromination or chlorination of an alkyne is not exactly the same as the mechanism for the alkene. And so the most likely mechanism for that is the pi bond grabs the bromine, kicks the bromide off, and you form a carbocation. You form the carbocation on the more substituted side. And then the bromide adds. It can add either cis or trans to the bromine, but since hydrogen is smaller than the bromine, it has a tendency to want to add to trans to it. Like so. But this accounts, the small amount that adds cis to the bromine accounts for the formation of that minor product. And it's believed to go through this type of intermediate as opposed to the bromonium, mainly because this molecule right here is too strained to exist for any period of time. If it does form, it rapidly becomes the carbocation. Okay. Now, with that, that's pretty much all the reactions that are going to be on the third exam. We've covered them all. So, Friday, we'll probably just have a review. Please email me topics you want me to go over on the review. And don't forget that Wednesday, the quiz is due by 5 p.m.